Welcome back. Here we are, ready to describe some data. Are you ready? I'm ready. Let's get into it. So today we're going to cover a brief overview of the types of statistics, descriptive versus inferential. We're going to talk about some measures of central tendency, some skewed data, some other probability distributions like the normal, binomial, and a few others. And we'll have a brief note on notation and differentiations. And of course, I will finish up with a little bit of R. So, first off, we have to describe some data. What do we mean by describing some data? What's the point? What's the purpose? So remember, statistics has one of two main types. We have descriptive statistics, which describe a data set, and then we have inferential statistics, which is hypothesis testing and is basically the second half of this course. For today, though, we're going to focus on descriptive statistics, which includes things like distributions, frequency distributions, percentages, measures of central tendency like the mean, median, and mode, measures of spread, which we'll talk about soon, like variance and standard deviation, and measures of association like correlation, which we'll talk about at the end of the semester. And in case you're really chomping at the bit and wondering more about inferential statistics, these are some of the things that we'll be doing in the second half of the semester. We're trying to make inferences about the population from our one sample. Remember, we can't sample everybody, but we can hopefully get a large enough sample and then use what we learned from that sample to make inferences about the population. This is the essence of hypothesis testing, determining associations like with regression analysis, comparing means, and comparing variances, all of which we will do in the future. But for right now, we're going to stick with descriptive statistics. First up, we're going to talk about some measures of central tendency. The mean, the median, and the mode. What are they? What do they tell us? And why would we use one over the other? Surely you're familiar with at least the mean, but let's look into them. Here we have the mean. It's just the average of a set, right? You add up all the numbers in a set, get the summation, and you divide by the number that were in that set. Here, the average would be 3. What about the median? Now, the median and the mode always confused me when I was learning this. I'd always forget which one was which. But if you drive, you know that the median is the thing that's in the middle of the road, right? It divides the traffic going this way from the traffic going this way. So that is a good way to remember that the median is the value in a data set where it separates the top 50% and the bottom 50%. So here in this data set, we have 222, 5, 6, 7, 7, and the middle value that cuts the top half from the bottom half in this case would be 5. See, it's right in the middle, that 50% of the data is above and 50% of the data is below that point. Now you might wonder, well, how do you get the median for a data set that that's basically even, that doesn't have a middle odd number? You would take the two values in the middle, add them, and divide by 2, and that would be your median. Now lastly, the mode, it's like, think of like modus operandi, the default, the fallback kind of thing. The mode is the most recurrent thing, the most recurrent value in a data set. In this case, we have a bunch of people scored a 2, and that is the mode of this data set, 2. It's also really useful, the mode is great for categorical data. So remember in one of our last videos, we talked about frequency distributions, and I had pretended to ask a bunch of people their favorite color, and 24% liked red, and red was the most common answer in that data set. So in that case, red would be the mode. So let's think about some of these measures of central tendency. And let's talk about money, because everybody likes to talk about money. What is the average income in the USA? First of all, is there anything wrong with the way I'm asking that? Is there a better way I could ask that? Think about that for a second. So let's look at what the average for the average citizen in the US would be. The mean income in the USA is around somewhere between 48,000 and 69,000, which is kind of a wide range, but bear with me. But how does this strike you? Does this sound about right? Considering all the people you know and the incomes they make, does this sound in the realm of realistic possibility? So then imagine you have all these average Joes, all these average Marys, they're all at their bar, and everybody in there is just having their average income and everything's chill in their average world. But then Bill Gates walks into the bar and everybody on average becomes a millionaire. Woo! Yay! Right? No? What? Well, as Bill is saying here, those are just bad statistics, because this is true. On average, if there were 10 people in a bar and all of them made about $40,000 or $50,000 a year, but then Bill Gates walks in, the average is going to skyrocket. But have everybody else's incomes skyrocketed? No, it's not the most accurate representation of the data. Here's an example of exactly that. Here are all the average Americans and their average incomes, and we look at the mean, and it's about $50,000. The median is about $47,000. Now, let's say that Bill Gates walks in. Here he is, being really rich. Good old Bill. The mean income is now pretty high, about 100 million, which of course has not changed. Nobody in the bar's income has changed that dramatically. But the median income, notice this, the median income has not moved at all. The median is still the median. So now in this case, would you rather report the mean or the median to get the average income level of most Americans? Especially considering what we know about the income distribution or the discrepancies in America, it's probably more appropriate to report the median. So what is this doing? When Bill Gates walks into this bar, what happens to the mean? It blows up, right? We have this one crazy outlier that is pulling all the data one way. It's skewing the data. And the mean is very, very sensitive to these really high numbers or these really low numbers, these outliers. So here we would have Bill Gates, let's say. And let's say most people's average income is, these are two different graphs, by the way. We're only going to look at this one for right now. Let's say that these are most people with their average incomes, and here's Bill Gates way over here, really, really far up that distribution. If we have average income, or excuse me, income here, he's way out here. So notice how the median in this case is less than the mean. The converse would be true if you had a really low outlier. Now these are called skews. And I used to always get confused about which part was the skew. Was it like the hump part or the pointy part? And then I remembered what a skew is, like a skewer. You know, just like skewering something. It's that pointy thing. So the skewer part is the part that's pointing. So let's look at this side where we would have a person who has a really low score, for example. Maybe everybody did really well on the exam and one person just didn't show up and they got a 0. Their score would be way over here and everybody else would be about here. And what would end up happening is that the average score would get dragged down by that 1 0. But the median is still pretty good, still solidly right here. So in this case, when there is a negative or a left skew, where the left is talking about the skew. Which way am I stabbing? I am skewing to the left. So it's a left skew or a negative skew. And in that case, it's because somebody had a very low value that's pulling it all that way. And it's always the case with left skews that the mean is going to be less than the median. Now, let's come back over here and look at Bill. Looking at you, Bill. So remember, average people here, one extreme value way out here, it's pulling that mean out of the frame. And it's skewing it this way. So now the skew is, I need like a fencing blade. So Bill has skewed everything this way. This is called a right or a positive skew because it's going to the right. And in this case, the mean is going to be greater than the median. So the average is going to be over-representing the average. Again, with the left skew or negative skew, it's going to be the mean that is under-representing the average. So if the income in America is skewed because of that top 1%, which it is, what does normal data look like? Let's look at some other distributions of data. Probability distributions. Here it is. Here it is, ladies and gentlemen. I know you've all been waiting for this one. Here it is, the normal distribution. Behold, behold. So this doesn't look like much now, but this is a very impressive, amazing thing. So let's get acquainted a little bit. We're going to see this a lot of times, and it's going to take a few experiences with it to get familiar with it. So first off, what's most important to notice is our axes. We always need to pay attention to our axes. On the y-axis, this is probability. So low probability, high probability. Over here, we have, they're all basically saying the same thing, but they're just like different languages saying the same thing. A translation. So one is in Spanish, one is in Italian, one is in French, and one is in Latin. But they all say the same thing in a slightly different way, but it's the same message. So here is where we're going to put possible scores, or maybe the income value of most people. This is going to be the scale that we're researching, the variable of interest. And here, always remember that this y-axis is actually the probability of seeing somebody who is average. So if the average is right here, boop, it's got the highest probability of being observed, right? Because it's the average value. Most everybody is average. So there is a very high probability of seeing somebody of that particular income level or that particular height, whatever it is the variable of interest is, if the data is normally distributed. So what is normal? What do we mean by normal? Well, we saw those skews and everything is stabbing one way or the other. This one, go back real quick, we see that it's nice and symmetrical, right? There is no heavy skewing one way or the other. It is symmetrical on both sides around the mean, so that means that there's just one big hump right in the middle. There are many, many examples of natural things following this distribution, like human height, temperature, heart rate, blood pressure. These are all very related to biological functions. There's many, many other things. There's also delivery time, grades, maybe even guesses. Lots of things will normally distribute over time if you do it if you sample enough people enough times. The typical value of something usually lingers or clumps right around that mean, and those, again, are more frequent. So the majority of females are around 5'4"-ish, with a few extremely tall and a few extremely short. So here is another we see another normal distribution here. Right here in red is the females, in blue is the males, and this is a distribution of height. We're looking at all the different types of height here. And again, this is the probability of observing, let's say, a woman who is about 5'4", 5'5". There is about a 16% probability of seeing somebody who is about 5'4". Look at the males, the average height is about 5'10", and the frequency of that is about 15%. So there's a 15% chance of seeing a male who is 5'10". Now let's look at some more extreme examples. Let's say that we're looking for a woman who is about, let's say, 6 foot, right here. Probability of that, it exists, it doesn't look like it, there's a tiny probability, it's about like a 1 or a 2% chance of seeing that. So that is, again, what this is saying, that here is the low probability if we were to climb across, and here's the high probability. Let's do one more. Let's say, gotta get close to see the screen. Say we have a 6 foot tall man. Let's go up about right here. Is about that probability, which is associated with about 8% chance of being 6 foot tall. So we see here the probability of a male, an average male height, and an average female height. As female heights get more extreme, so maybe like 6 foot, or much shorter, less than 5 feet and 4'10"-ish, the probability of seeing a woman that tall or that short gets a lot lower, and same for the men. So another way to think of these curves, which I know it looks a little funny, but think of them as like piles of people. Like you have to sort through all these people and you're like, oh, there's another female who's 5'4", let me put you here. Another female who's 5'5", put you here. And of course there's going to be a lot of those average height people, so they're going to all pile up in the middle. Then there's going to be a few people out here who are super tall or super short. Another example is like delivery times, that most deliveries probably take a certain amount of time and there's a little bit of wiggle room around that. And it's something like this that allows certain companies, I don't even know if they do it anymore, like pizza or maybe Jimmy John's still does it, not sponsored, that if the time is within this window, you know, you still have to pay for it, but if it takes longer than that, it's free. But the probability of it taking that long is really, really small. That's why they set up these windows to make sure that they're within that time frame. So there's a few other types of distributions. We just saw the normal one, which involves the one hump right in the middle and it's symmetrical. There are many, many others out there. Another one, for example, the bimodal distribution. So remember, what's a mode? It's basically the clumped area, and if it's bimodal, that means that we have two. So there's one hump here and one hump over here. What kind of data could produce something like this? Can you think of anything in your world where you might see data like this? Take a minute. All right, how about this? Who shops on Amazon? Sometimes user ratings can be one of these examples where you either really love something or you really hate it. And that's mostly because people who are motivated enough to go leave a rating, it's because they feel very passionate, either positively or negatively about it. So sometimes you get things like this, where a lot of people will rate it as really poorly, a lot of people will rate it as really highly, and then people who are lukewarm about it just don't take the time to even rate it. This can also happen when you have two distinct groups, but you're not aware of it. So imagine that I took this data, but I didn't separate them by male and female. You would have these two kind of strange, distinct humps and would maybe wonder what's going on there. But then when you realize it's because of the differences between males and females in height, now you realize there's just two groups. This can also happen with clinical versus non-clinical populations. If you're measuring a group of people who have been diagnosed with generalized anxiety disorder and you're giving them some sort of anxiety test, and then you have another group of people who have not been diagnosed with generalized anxiety disorder, you might see two distinct humps from their scores. Another type of distribution, this one is called a uniform distribution because they are all uniformly equal and even. Also called a rectangular distribution, but I've always heard it called uniform. And this basically means that every single possibility has equal probability of occurring. And something like a pair of dice or a die can do that, right? You can get a 1, 2, 3, 4, 5, or 6, and each side has equal probability if it's a fair die. So there is a 1 in 6 chance for each one of them. There are many different types of probability distributions that are used for different types of data. These are just a few of them. We have the normal, the binomial, uniform. There's also a thing called a Poisson, the Bernoulli, and the list goes on. But for the rest of this course, we're going to mostly focus on the normal distribution because it's a little bit more intuitive and so much of nature follows the normal distribution. Now, the point about all these distributions is that all distributions help us to quantify and determine the probability of seeing a particular thing, a certain observation. Again, like the probability of seeing a woman who's 5'4" is about 0.18, so about 18% chance. Now, that might seem a little bit negligible or erroneous right now, but in the future, especially with hypothesis testing, this gets really important. We want to know the probability of seeing certain things. So we're going to just have a quick note about notations and differentiations because it matters if you're talking about a sample or a population, the type of symbols that you're going to use. So now that we're finally starting to dive into the numbers, we need to make sure that we label them correctly so that if anybody else was going to read this particular number, they understand that it came from either a sample that you took or the entire population was asked, and this is the average for the whole population. When we design a study, we first define the population of interest. So let's say, what is the average level of stress for all college students in America? Who is our population of interest? All of the college students. Reality check though. Can we ask every single college student in America their level of stress? No. Instead, we're going to have to take a sample from the population. And again, it's very important that whoever reads our statistics or any statistics you read, you can know, did they ask everybody of a population or did they take a sample? So a little bit on wording, we have different vocabulary for the numbers depending on if we're talking about a population or a sample. So parameters are when you're talking about populations, and statistics are for samples. Now you might be wondering, what is a parameter, or technically what is a statistic? So if you were to take the average of a sample, that is called a statistic. That sample average is just a type of statistic. There are many, many different statistics you can calculate, but that's just one of them. Now, if instead you were getting the mean for an entire population, let's say my population of interest is just my statistical literacy course, I can ask all of you, and that is the population. Now, if I'm talking about that, I'm going to call that a parameter. It's still an average. They're both still an average of something, but when I say the parameter, I'm talking about the population's mean. When I say a statistic, I'm talking about the sample's mean. This may seem a little bit arbitrary, but it is important to differentiate between the two so people know what you're talking about. So how do we know which one we're talking about? In statistics, you'll sometimes see the normal common letters that we think of, like the Roman alphabet, and sometimes you'll see things that look like ancient Greek because they are actually Greek. These variable distinctions tell you if you're talking about an entire population or just a sample from that population. I just want to introduce you to this notation. So when we're talking about a population, we're talking about what's included in it, the complete set, everybody in that population, not just a sample of them. If we're talking about a subset from the population, we're talking about a sample. If we're trying to get the mean of a population, that is actually called mu. That's what this symbol is, and this is how you pronounce it, mu. And if we're talking about a sample, we technically write x bar, called x bar. I should also say that we normally say the mean, but in notation it is important. Like, there will be quizzes about this, so you do need to understand the different types of notation. Then we have a thing called like sum of squares. That's going to be the same for both. Then for variance and standard deviation, we use a sigma or sigma squared. And for samples, we're just going to use the letter S. For sample size, sometimes people will use a big N to denote the entire population. And in samples, it's usually a small n, but this is not always adhered to. And then the numerical descriptor, what do we call these things? We call them all parameters, because parameters are for populations. And what do we call these when we're talking about a sample? We call them statistics. So now that we know how to describe some data and measures of the centralness of data, the averageness of data, next we're going to quantify the average amount of difference and spread in a data set. Basically, on average, how different is everybody from the mean? And that is going to be variance up next. I'll see you there. Peace. And now, one little snippet of some R, calculating the mean and median in R. So it is quite easy when you do this in R as opposed to trying to do all this by hand. The most tedious part about doing it in R would have to be something like this, where you have to type in all the data. But let's say I have some height of people. So right here, I'm going to create a data set, and I'm going to call it height. And I'm creating it by using this little arrow thingy. I'm going to assign whatever I write over here, I'm going to assign it to that name. So I'm basically labeling all this over here with this name. These are all different heights in inches, so like 64, 62, etc. Now when you make a list like this, you have to put a little C in the front. It stands for concatenate, don't worry about that. C parentheses, and then you can type all your numbers with commas between them. And you run that, and now you have an object called height, and it has all those numbers in it. And now that you have that, pretty much all the hard work is done. All you have to do is say, hey, R, give me the mean. Just type mean, M-E-A-N, parentheses, put the thing that you created into that mean, pops it right out for you. And we can also get the median if we want. There is no quick way to get mode, but there kind of is, but we'll talk about that in the future. And while we're here, we can also make a little histogram and a little box plot. Check it out. Very, very simple with our data. So notice, this is some kind of normally distributed data because these are different heights of people. So it has that nice little hump. Now it's not perfect because it's a small sample size. There's only, I don't know, 10 to 20 observations there. If you were to get hundreds of them, this would start to get smoother and smoother. And this over here is called a box plot, which we will discuss soon.